So our next speaker is Sam Oliver of the United States Geological Survey, and she'll be talking on process-guided deep learning for decision-ready predictions.
Thank you. I just have to figure out how to unmute myself and get my slideshow back. Can you all hear me?
We can hear you and see your slides.
Great, thanks. Yeah, so today I'm talking about process-guided deep learning for decision-ready predictions. My name is Sam Oliver. My pronouns are she, her, and I'm a data scientist at the US Geological Survey. If you saw Jordan Reed's talk yesterday, that was a great introduction to this collaboration, which has been fueled by a long-term collaboration with Vipin Kumar's group at the University of Minnesota and Xiaowei Jia at the University of Pittsburgh. So what is the decision I'm talking about today? I want to focus on management decisions in the Delaware River Basin and how we can use process-guided deep learning to improve those decisions. To orient you, the Delaware River Basin is located in the Northeast United States. And in this basin, there are a series of reservoirs that serve a variety of human needs, including flood control, recreation, and drinking water. The reservoirs that get the most attention are those in the upper basin. Up here, those are owned by New York City, and they provide drinking water to over 15 million people in and outside of this basin. Water from these reservoirs is remarkably moved about 130 miles from the reservoirs through an aqueduct system. And these reservoirs have highly protected forested watersheds. The water from these reservoirs is clean enough that it can be provided unfiltered to the taps of New York City residents, which saves the city millions of dollars each year. There are several competing demands for these water resources in the basin, and one of those for water in the reservoir is to maintain the world-renowned trout fishery in the upper basin. Trout and other species are sensitive to high temperatures, and part of the flexible flow management program in the basin states that temperatures at the Lordsville gauge, which is in the upper basin, must remain below 75 degrees Fahrenheit. Of course, there are various things that threaten to push water temperatures over 75 degrees, one of which is climate change and the observed increases in water temperatures both here in the basin and around the globe, but also things like land use change. But fortunately for reservoir managers, they're able to utilize the deep water release from the hypolimnion, or the cold water layer of the reservoir, to maintain downstream temperatures. The number of times the reservoir operator needs to make this decision is variable and based on weather. You can see here from their website, this is all of the days they made a thermal release. In 2020, it was very warm, and they had a number of extended expected exceedances where they were required to make a decision about releasing this limited amount of water. So the thermal bank is the set volume of water. It resets every water year, and so there's incentive to conserve it and make good decisions about whether or not you need it. So how do we go about modeling downstream water temperature from these downstream from these reservoirs? As Sharu just pointed out, it's difficult to model stream temperature below these reservoirs. But first, I want to talk about what decision ready means to us in this context. So first, we needed to make predictions that had good enough accuracy and reliability to meet our stakeholder needs. We needed to deliver these forecasts at the time that they are needed. So daily, the reservoir operator is making decisions about what volume of water to release tomorrow. And the predictions also needed to contain the right information. Predictions from the model needed to be condensed in a way that was useful to the reservoir operator. The approach that we're taking to deliver decision-ready predictions is, of course, by using knowledge-guided machine learning, which is why we're here today. I'm not going to talk a lot about these methods that we built on, but I highly recommend this paper that I've linked to. As I said, our collaborator, Xiaowei Jia, published this paper earlier this year, and it has a lot of great context for this modeling effort. But I'll mention two things. First, a graph convolution network was used to leverage information across the stream network. And this helped improve performance across the Delaware River Basin for stream temperature, which is shown in this sort of pink distribution that you can see in the background. Second, we used pre-training on predictions from a process model to also inject process into our deep learning models. In the case of streams, we used predictions from the precipitation runoff modeling system, which was coupled with a stream temperature network model, which is a coupled flow temperature model that predicts temperature by solving a heat budget and sort of encodes our understanding of physical processes in the system. We use these predictions as truth, and we penalized the model when it made predictions that weren't similar to the predictions made by the process model. And in this way, the deep learning model is able to emulate a physical model before it ever sees real temperature observations. And you can see from the yellow distribution how that pre-training improved our ability to predict water temperature in the basin. So how do we go from Xiaohui's work in that publication to decision-ready predictions? Well, it'll take a lot. We needed to understand the specifics of the decision itself and how we needed to change our modeling approach to meet those criteria of the decision. For example, what is the decision cadence of the reservoir operator? What time of day are they issuing forecasts? And therefore, what's the latest possible time we can run the model? What's the latest possible time we can grab temperature observations from the real-time USGS network? What are the relevant locations in the Delaware River Basin where they want to know what the future water temperatures will be? We needed to automate these processes so that we could deliver them each day. So all sorts of different developments needed to happen in order to make these quote unquote decision ready. But there were two major pieces missing from our PGDL modeling framework that we've recently addressed that I want to highlight today. Those were improving our temperature predictions below reservoirs, which is a challenge, and also building data assimilation capacity into our modeling framework, which allowed us to incorporate the latest information to improve our predictions. So this is a graph of daily water temperature observations for a year in the Delaware River Basin to sort of demonstrate the problem of predictions below reservoirs. So the yellow line is showing you water temperature observations from a stream near Philadelphia. It's one of the warmest segments in the basin. And then the blue line is showing you temperature observations from below a reservoir. And you can see they look very different, just sort of high level. The reservoir observations are much cooler on average, except for, of course, the shoulder seasons, where the reservoir reaches are actually warmer than stream reaches. And you can see these bizarre signals of the reservoir releases that are sort of representing three major processes: stream temperature processes, reservoir temperature processes, and then human decision making, which is really difficult to model. Lucky for us, the collaboration between USGS and our academic collaborators to model water temperature started in lakes, and Jordan Reed and others demonstrated that pre-training on process-based lake model predictions could improve predictions across all spectrums of data availability, which you're seeing in this figure. Similarly, in streams, the methods I just talked about from Xiaohui's paper, adding knowledge into our machine learning framework improved predictions across the Delaware River network, and particularly in places where we don't have a lot of data. So we started with Xiaohui's stream temperature model as a starting point, but we still had a lot of work, of course, to do in order to represent reservoirs. So like I said, our group had experience in both lakes and streams. So our first thought was we need a better pre-trainer. Right now, our PRMS SNTemp pre-trainer is sort of, it's a natural flow model. It's not aware of reservoirs. And so we need a way to represent reservoirs. How do we get that into our process model pre-trainer? So we knew we could relatively easily spin up both a reservoir and stream process model. We did that, and then we asked ourselves, how can we combine these two models? How do we present this combined information to the neural network as a pre-trainer? And how do we do this in an efficient way? We don't want to take months to years to develop, say, a fully coupled process model. So how can we do this quickly as well? We landed on a pretty simple statistical method where we assumed that the relative influence of the reservoir temperatures would decay as a function of distance downstream from the reservoir. We fit an exponential decay function shown right here to existing stream temperature data below 2 reservoirs in the basin, Pacton and Cannonsville, to calculate the decay rate as a function of distance. So right below the reservoir, or distance set to 0, we weighted the reservoir predictions by 1 and the stream predictions by 0, and so on. And this figure up here is showing what that looks like over different distances. So closer to the reservoir, say at 10 kilometers, those reservoir predictions are weighted very heavily and look very similar to the GLM predictions that are predicting water temperature at the outlet depth of the reservoir. Closer to the stream, so say, further downstream from the reservoir, those predictions would look much more similar to PRMS SM temp predictions, where we assume the processes look more like stream temperature processes, and we downweight the reservoir processes. So how did the simple statistical combination of these two models improve our pre-trainer? Well, in conclusion, it did. This is an example of a site 15.8 kilometers downstream of the Cannonsville Reservoir. And you can see, especially compared to the gray line, which is our PRMS SM temp predictions, the combined model, which is shown in the blue line, greatly improves our predictions. And you can see the observations are there in black. So immediately downstream of these reservoirs, it about halved the root mean squared error of our predictions. So we're confident that this is going to give a better start to our deep learning models by pre-training with this combined statistical model. Okay, so we've made some progress on representing temperature dynamics below reservoirs. How do we accomplish this next point, which is incorporating the ability to include the latest information, so real-time data to improve our predictions. And we did that via data assimilation. We know that data assimilation is already happening in the heads of the reservoir operator. And the goal of this exercise was to formalize that into a modeling framework that would help us improve predictions. So on each day, the reservoir operator is using different pieces of knowledge about whether they should release water or not. And again, we're trying to formalize this process. In this case, the reservoir operator already had a model that was doing 1 day ahead forecasting. And so they have that model in hand to tell them what they think the temperature will be tomorrow. They can also look backwards at yesterday's temperature. How warm did it get yesterday? What was the weather forecast yesterday? Does that help me inform my decision today or tomorrow? The reservoir operator also has a sense of how that model is performing. They might think that weather forecasts in the upper basin are really crappy, and they know it usually rains more than the forecasts say it's going to. They might know that their temperature model historically over predicts in certain conditions. And so whether that's a formal bit of knowledge or it's all in their head, they're using that information to make decisions. So from a modeling perspective, what we want to do is say, okay, here we are, we're on day 0, we're trying to make a forecast for tomorrow. Let's look at how the model did yesterday. Well, the model is nearly perfect. Let's just trust the model and push forward and make tomorrow's prediction. When we move to tomorrow and all of a sudden the model does very poorly, we might want to nudge that model a little bit so that it makes better predictions into the future. And so the way that we did this was adding data assimilation to our deep learning framework. We started with a base LSTM that makes predictions of stream temperature based on meteorological drivers from today and information about the system passed on from yesterday. And I'll note that this model is pre-trained in the way that I described earlier. When we assimilate observations into the model, we are updating the temperature predictions and cell states of the LSTM model with an ensemble Kalman filter to adjust for any errors in the model, which then get used to improve predictions at the next time step. From a practical perspective, this is sort of what the modeling framework and inputs and outputs looks like. Each day, our pipeline is retrieving and processing weather forecasts from NOAA product. And we're also going and fetching observed reservoir releases and observed water temperatures from yesterday. And forecasts are made for today, day 0. because we haven't observed today's maximum temperature yet when we need to issue the forecast, and then forecasting 7 days out into the future. From 3,100 ensembles that are generated using the guest ensembles and dropouts, we're able to produce an estimate of water temperature forecast, but also produce those confidence intervals as well for 5 relevant sites in the basin. And then, of course, we need to take this information and translate it into something that is useful and digestible for the reservoir operator. And so I wanted to just show you what this looks like, because it might look very different than what we might say publish in an academic publication. So this output was co-designed between us and the reservoir operator and contains the information that they need. In this case, they needed the forecast with confidence intervals at these 5 sites. But they also wanted that forecast translated into the probability of exceeding 75 degrees, because that is the most relevant piece of information to the decision that they're making. We also report reliability and accuracy so that the operator can determine whether these forecasts are useful to them. Can they trust it, and is it accurate enough to inform their decisions? Notice we're providing lots of information here on the request of the reservoir operator. We're looking 10 days in the past. So how is the model performing recently? And then how has it done historically over the duration of the forecast? This is actually a real forecast that was issued yesterday. So how are the models performing? Overall, the deep learning model with data assimilation is performing well. We're able to maintain below 2 degrees RMSE for 7 days into the future. And we have about a 1.2 RMSE on 1 day into the future. I'm showing you the persistence forecast in purple here, which is sort of the easiest model, which is just taking the temperature from yesterday and propagating it forward. The deep learning model in orange is using yesterday's temperature as a predictor, as a driver, and then DA is assimilating information. You can see that there are marginal gains from the data assimilation approach, but it is helping us generally on day 0 and day 1. And then I just wanted to show you that there is variability across these 5 sites at how well the models are performing. The most decision relevant site is this Lordsville site in green. And I'll note that the hardest site, the site that's performing the worst, is below the Never Sink reservoir, which we have yet to model and include a new pre-trainer for. So one hypothesis is that once we include that new pre-trainer, we can improve performance. Of course, reducing those predictions down to an RMSE or a bias estimate is sort of covering up some of the nuance that we see in the data. One thing that we've noticed is that we are over predicting when there are large rain events, which I've highlighted here. And we think this is because we've had to remove precipitation from the drivers of the model, because when we were developing the model, it was actually making predictions worse. So the model currently has no way to distinguish between flows from reservoir releases and sort of flows that might be generated by precipitation events. So we're hopeful that once we get some new driver data in there, that will help improve forecasts at some of these sites. So I want to end on a few lessons that we've learned from taking PGDL methods that have been developed between us and our academic collaborators to delivering predictions for real-time decision-making. First, I'll say that the specifics of the decision are really important and can constrain your modeling efforts. When we learned that we needed to issue the forecast at 11 a.m., all of a sudden we lost some performance because we could only look at yesterday's maximum temperature and not today. So really understanding your decision landscape and what they want out of that decision can be really important, and can be helped through co-design of these products with your stakeholder early on. Another lesson we learned is that we needed to train the model up to the forecasting period. And sometimes that can be difficult to do because it's hard to track down all of the driver data up to your forecast period. So for example, it was difficult to get together all of the reservoir release data because those aren't easy to get from the reservoir operator. So that might be something that slows you down in getting a forecast up and running. And finally, traditional model outputs or evaluation metrics may not be the most relevant thing to the decision maker. One thing we're really excited about is looking backwards over this first summer of forecasting that we did and ask questions like, how well did we anticipate exceedance events? Our next steps for these forecasting efforts, we rapidly kind of deployed this forecasting effort. So we have a lot of model development that we still want to do. Like I mentioned, we want to expand our drivers into flow and or precip. We want to do uncertainty quantification. We also recognize that we're leaving some information on the table. We're leaving 10 hours of temperature data in the morning on the table, and we're wondering how much we can improve our predictions by understanding, say, the minimum that occurs in that time period. Maybe we have to do sub-daily predictions, we don't know. I also left out that we're actually not using the graph network for these predictions because we're just doing 5 individual sites, but we're interested in spatially expanding and going back to that graph convolution network. And finally, we want to make these forecasts public and useful to more than just the reservoir operator who we're sharing them with privately right now. And so hopefully in the near future, you'll be able to find them on this Office of the Delaware River Master webpage that I'm showing here. And thank you, that's all I have.
Great, thanks so much, Sam.